Hi guys, this is a special session to supplement our class, okay, for the students who want to learn more. In our class, we have studied bubble sort, right? Some people say bubble sort is hopeless, which is not necessarily true, okay? Bubble sort can still do a good job to sort a small amount of numbers, okay? There's nothing wrong with bubble sort in that case. Okay, so do not underestimate the value of bubble sort. It's not a waste for us to study bubble sort, all right? But we have to admit that if we have a large amount of numbers to sort, bubble sort will not be efficient enough, all right? We need more efficient sorting algorithms. For example, Quicksort, all right? So in this special session, I'm going to introduce Quicksort to you. By the way, the Quicksort algorithm seems to be a very much popular interview question, okay, given by Google, I heard about that, by Microsoft, I have seen that, all right? So probably the Quicksort algorithm will be one of the most important algorithms in your future career life. Right? So it deserves more attention from us, all right? So Quicksort, it is. To study Quicksort, we will need to employ a totally different idea or different way of thinking about the sorting problem. Okay, the specific way, the very special way is so-called divide and conquer. This figure is from one of my papers, quite important paper. It means a lot, at least to me. So I put it here as a souvenir. It's simple though. This is divide and conquer. If we have a big and complex problem, we can try to break the original problem down into smaller problems. Then we come up with smaller solutions to address those small problems. And eventually we can compose the small solutions into a bigger one, okay? A bigger overall solution to the original big and complex problem. All right, this is divide and conquer, very straightforward. And it's very common and probably a very ancient strategy for human beings to deal with real world problems. Maybe you have used it without being aware of it. So what about sorting problem? Well, we can definitely use divide and conquer strategy or idea to deal with the sorting problem. Imagine we have a large amount of numbers to sort. We can break it down into smaller groups. Each group have much less numbers than the original one, and even intuitively thinking, it'll be much easier for us to sort those small group numbers, right? Makes sense. So it's definitely suitable. It's definitely suitable in the sorting problem, okay, in this divide and conquer approach. And of course, we can build up formal algorithms to address the sorting problem in the divide and conquer way. For example, let's have a quick look at the example. Firstly, we have a set of numbers. Just imagine we have a large amount of numbers. Of course, although they are not, right? It's a demo. So we imagine we have a large amount of numbers. And intuitively speaking, we can split it into multiple groups. Let's say split it into 2 groups. Or we can make it, naturally speaking, we can cut it down into half and half. And we will have 2 groups, smaller groups. That's one way. Yeah, it's true, it's possible. But what about we use a better way? How about we use a better way to fix this, to split the original set of numbers into 2 parts? All right. The better way is that we pre-select a reference from the data sets, and we name it as pivot. Actually, it's just a reference number, especially in the context of this special session. We don't have to consider any special meaning of it. It's just a reference number. But we follow the naming convention, we name it as pivot. How about that? Reference number. And the reference number can be any one among the set of data, okay, the set of numbers. If you select a middle one, doesn't matter, you can move it to the right-hand side, all right? And it'll look like exactly the same, all right? So it's a generic stuff. The pivot, the reference number is a random one, okay, a random one. For now, we decide for our convenience, we select the most right one. Now, we specify that there's a rule to divide the original numbers into two groups. We select smaller numbers into one group and select the bigger numbers into another group by referring to the reference number. Okay, this is actually a better way. So in this case, we can select smaller numbers than 9 into, let's say, a left-hand group, and we select the bigger numbers than 9 into a bigger number group. That'll work. So we can have the specific numbers and make the description more generic. It'll be like this. We have a smaller number group, and a bigger number group, and then we put our reference number in between. Okay? Then we will have sub-problems to solve. For now, we have two smaller problems, right? Then in the next step, or in the future steps, we're going to sort the numbers in the left-hand side group, and we will sort numbers in the right side group. After that, the numbers will be sorted, right, in total. And to follow this strategy, we can keep dividing those groups, right? We follow the same strategy. We select another pivot from the left-hand side group, and then we use it as the reference number to further split into two smaller groups. Okay, left-hand side smaller group has smaller numbers, and then we have relatively bigger numbers than the new pivot. We do the same thing for the right-hand side group. For the right-hand side group, we select a new pivot, and we cut the original data set into two groups, smaller groups, relatively smaller numbers group, and a bigger number group, until all the groups, subgroups, will have a single number, which means until we all have a single number groups, just like this, we can stop. Because the single number is already sorted. We can imagine it this way. Then we leave it as it is. We keep it as where it is. Okay? And after that, we can imagine we can keep those individual single member groups as they are. The original data, original numbers are sorted in this way. So following this observation, we can quickly see a recursive process, isn't it? When it comes to the recursive process, I remember a previous student used to give me a comment saying that, hey, teacher, I'm recursively confused about recursive function. Okay, because we know we need a recursive function to describe the recursive process. Indeed, it's very confusing because the recursive process is kind of easy, relatively easy for us to recognize, but it'll be much more challenging for us to describe, which is true. Then how about we only focus on one step, all right? We only focus on one step. We only focus on the first step of this recursive process, and we only describe this first step, all right? Forget about the recursive process. Forget about the confusing recursive details. That will be easier to describe, right? If you have attended my previous lectures and if you have played the Hanoi Tower game with classmates in my class, you should be able to immediately remember what I'm saying here. We have a slogan, we have a magic approach, inside out, to describe the recursive process. Okay, if you don't know this, doesn't matter. It's very straightforward. We can quickly go through this, and you will see what it is. All right, and by implementing this sort of the inside-out magic slogan or strategy, we only need to focus on the first step, and we imagine this step is a magic step. we can use a magic function to satisfy the functional requirement at this step. And this magic function will perfectly fix, by satisfying the functional requirements, our magic step will perfectly solve the original problem. We don't need the rest of the recursive process. We can solve the problem only at the first step. How about that? That's why it's a magic step. And we use some magic function to satisfy the functional requirement. In this case, we need to, in the following recursive processes, we will sort the numbers in the left-hand side group, right? So this is the function requirement. Let's say we have a magic function to do so. And for the right-hand side group, we will have the same functional requirement. We need to sort the group members in the right-hand group. Well, we have a magic function to do so. Don't worry about that. Then we can describe the step only. We describe this step without worrying about the recursive process. Okay, let's have a try. Firstly, we have multiple numbers. All right, of course we need multiple numbers. We just mentioned if there's only one number in the group, we can stop there. All right, so now we have multiple numbers. Firstly, we need to split up into two groups, right? Partition the group into two groups. For our convenience, we name it as group left and group right, okay? And don't forget, by referring to the reference number, it's pivot for now. So we have a specific requirement here, although we can't specify, we can't write it down here on this slide, but we need to keep this in mind. We have a left-hand smaller number group, and we have a right-hand bigger number group, right? And the pivot will stay in between, all right? So we have the partition activity. What's next? We will have a magic function to satisfy the functional requirement, which is to sort the left-hand group's numbers. All right. Previously, we have a magic player. Now we have a magic sort. Doesn't matter. It's a magic function. It does this functional job perfectly in the black box. We don't know how, but it does. All right. Then we have the same function to satisfy the right-hand group's functional requirement because they have the same functional requirement actually, but with different data. So the same. After this, we claim that we have fully described our first magic step. Okay, if you got confused, you can pause the video and double check the previous slide. Think and rethink these activities at the first step only. Okay, it's much more easier to understand. Now, the following question is, well, I have described the first step, which is good. And we use the magic function to do so. That's from our imagination. We don't have such a magic function yet, which is true. That's where our magic slogan comes from, inside out. Given our procedural code described a magic step, how about we treat this description as a functional body? It's a function body inside the magic function itself. Then we go outside to define this magic function, okay? We can follow the syntax of whatever language to describe this function. And we use exactly the same name because this is the name we just used. Okay, we just used. So when we define it, we should follow the syntax to have the same function name. And then because we have used this function, we have decided what type of information we decided to input this function. So it'll be very convenient for us to decide to design what type of parameters, how many parameters we're going to use in the definition of this function. Okay, so inside out. All right, inside out, this is a very useful strategy for us to construct recursive functions in a generic sense. Keep this in mind, keep this slogan in mind, okay? It's very useful. If you're interested, if you haven't done so, you can have a try with the Hanoi Tower game. It's very interesting. All right, you can have a try. You will see the magic here, okay? Then how about we define that this recursive function as a MagicSort algorithm, because we, after having this recursive function, we can claim that the previous recursive process has been described. And after describing the process, it's definitely an algorithm then. So what about we name it as an algorithm, MagicSort? Of course, there's no such a name of MagicSort. It's a made-up name. We don't have such a name of MagicSort, although we have similar algorithm, sorting algorithm. But it's not a Quicksort algorithm yet. It's a MagicSort. Okay, it's a different sort. It works, still works. It'll work. You can manually try because our human beings' eyes can quickly identify which numbers are smaller numbers, which numbers are bigger numbers. So you can manually select the smaller numbers without worrying about the sequence. All right, grab smaller numbers into the left-hand side group and grab the bigger numbers into the right-hand group, and then manually going through this process, you will see how it works. Okay, magically works. So indeed, it's a real sorting algorithm there. But of course, given different implementations of the partition, we will have different versions of MagicSort. For example, we just described we can intuitively split bigger numbers and smaller numbers, right? So we can also define some rules to partition the numbers into those two groups. For example, we can use a very inefficient way. We can screen the numbers from left to side all the time. Every time we screen this way, we screen the numbers in this way. We can still split those numbers into two groups, right? And we can also use probably the most efficient way that Quicksort employs. All right, we will introduce that later. That will also be a way of partitioning numbers. See, by using different partitioning implementations, we will have different versions of MagicSort. And now I can tell you that Quicksort is just one of the versions of MagicSort. So what we need to focus now is on partition only. All right, so we can narrow down our focus on partition now. I'm not sure if you have heard about that or not. Some people also claim that the partitioning process is also a confusing part of Quicksort, which is true. But we can make it easy to understand by considering the partitioning process as a two-group negotiation. All right? Let's imagine we already have two groups. Okay, still group left and group right. And they have different interests. Group left is interested in small numbers only, and group right is interested in big numbers only. But at the beginning, before we have a reference, okay, before we have a reference number, we don't know how we decide what number is small, which number is big. So they share all the numbers with each other. All right, they share all the numbers with each other, although they have different interests. Then for some reason, we suddenly have a reference number, pivot. All right. After setting up a reference number, these two groups are crazy for pivot. Both of them want to have pivot exclusively. Then let's have a negotiation. Okay. Those two groups decide to negotiate with each other about having pivot exclusively. All right. So in this case, to make the negotiation a fair play, we let group left talk first. You see, the location of the pivot really doesn't matter. If we put the most left-hand side number as pivot, as a reference number, we can let the group right to talk first. All right, but it really doesn't matter. But in this case, let's assume we have a pivot here, and we let group left talk first. Okay, your turn. Go ahead, negotiate. Then group left says, well, I want pivot so much, all right? So how about you give me pivot, and I will use a big number to exchange pivot, okay, as a compensation. So I will give a big number to you because you are interested in big numbers. And for my convenience, for our convenience, to prove that I'm not cheating, I will select the big number from my most left-hand side. Okay, instead of randomly select the big number, from our overlapped group members. All right, look at what I'm going to do. Firstly, I will screen the overlapped numbers from left to right. Now, firstly, I see 6. 6 is a small number. According to the reference number, small number is mine. Group right is not interested, so I can keep it without any problem. And then I see 7, still a small problem, so I can keep it exclusively with no problem. 5 is the same. All right, 5 is the same. We don't have to negotiate with that with each other about it. Now I see 11. Okay, 11 is a big number. How about you gave me 9? I will give you 11, and you can have 11 exclusively. I quit from 11 totally as an compensation. How about that? Allow me to have pivot exclusively. Group right says no, because we still have overlapped members, so I still have chance to negotiate. I'm not gonna give up, so I will follow your same strategy, but I will choose the most right-hand side small number to exchange pivot. All right, from our overlapped members. Okay, so I will follow the same strategy as yours. So firstly, I see 10. 10 is a big number. You are not interested. I have it exclusively without any problem. But now I see 3. How about I give you 3? You give me 9. And I officially announce 3 is yours. Okay, please give pivot to me. Let me have pivot exclusively. No way. Group left still disagrees. But because there are still overlapped members, so they can still continue the negotiation. So group left says, well, look, another number exactly is a big number in our overlapped numbers. So how about I use it to exchange pivot? Give it to me. Pulls pivot closer to itself. And then officially announce 12 belongs to group right. How about that? I disagree as well. Group right size, okay? Because I still have chance. I still have something to exchange. So I'm not gonna quit. I'm not gonna lose pivot so easily. So the same strategy. I screen the overlapped members from right to left. Firstly, I see 14. It's not negotiable, right? It's mine. You're not interested at all. Now I see 2. How about give me 9? I will give you 2 exclusively. Now, let's finish this negotiation, all right? Since there's no overlapped numbers except for pivot, okay? It seems we have to stop this negotiation. Fine, but nobody wins pivot. What's next? What should we do? Well, the both groups decided to sit down, to calm down, and both agree to quit from pivot. Okay, you have your exclusive group of numbers, and I have mine. Let's just stop fighting for pivot. Okay, for peace. For peace. Now, after this negotiation, we can see that the numbers are naturally kind of split, partitioned into 2 groups. Okay, see, it's not that difficult to understand then. It's not that confusing as long as we use this process of negotiation to understand the partitioning. Or you just imagine there's a negotiation process. So how about we use procedural code to describe this negotiation process? All right, forget the partitioning. We are just negotiate with each other. Now we have a set of numbers shared by 2 groups by default. Now let's negotiate. Okay, firstly, we have overlapped numbers. At the beginning, yes, of course, we have overlapped numbers. Please note the plural members, all right, which means we have more overlap members than just a pivot, all right? So we can negotiate. In our case, remember, just rethink what we have done. Group left talks first, grabs pivot to itself, closer to itself, and gives its most left-hand side big number to group right. And then if there are still overlap members, group right will never give up. As long as there are still overlap, group right will never give up. It pulls pivot again closer to itself and gives its most right side small number to group left. All right, then they will negotiate like this over and over and over again. Right, and eventually, if there's only one overlap atom, which is pivot, they have to stop anyway. They have to stop anyway, and eventually they gave up. We both gave up pivot. Okay, it's meaningless to keep fighting for it. Okay, and as a function, we can just return the location of the pivot because it perfectly splits those two groups. It indicates the end of left group because it's just next to the left group, and it indicates the starting point of the right-hand group, right? Right-hand group is next to pivot. So this is done. This is done. So how about we define this negotiation algorithm as algorithm partition, because eventually we use this negotiation to partition the numbers into two groups. That's the main purpose. But we use negotiation to help us better understand the strategy of the partition. And this strategy is exactly used by Quicksort. Now, we can easily define what a Quicksort is. A Quicksort is a special version of MagicSort by implementing a special partitioning approach. It's the negotiation-based partitioning process. Okay, see, it's not that difficult to understand. Now, I know the text might be too small to read, so you can review the previous slides to double-check the procedural code. Since we have finished describing the process of Quicksort, it's your job now to use whatever language to implement the Quicksort algorithm to make it functional. All right, by giving some example data sets, you will see how it works. Please pay more attention to the indexes. That'll be an interesting places. Okay, probably you will meet some troubles. Especially be very aware of the boundary conditions. But this is a perfect exercise for you to practice indexes of arrays or lists. All right, if you use Python, so practice it. All right, and if you're interested, bring your implementations to me. We can further discuss the theoretical features of Quicksort and even some disadvantages of Quicksort. Okay, that'll be interesting. So that's all. Enjoy the algorithm of Quicksort. Good luck with the implementation.